Hello everyone, welcome to examples video number 3 for Computer Science 230. This time we'll be going over power sets, and functions, going over 4 curated examples, as well as one final example which I'll be attempting to do. As always, please try to do these questions beforehand, and with that, we'll get right into it. Alright, going on to the first problem, we have to prove that A union B is equivalent to A symmetric difference B union with A intersection B, which is equivalent to A symmetric difference B symmetric difference to A intersection B. There's a couple different ways you could go about doing this, so let's just call this X, Y, and Z because that's a mouthful to say again. If you have X equal to Y and Y, or my bad, not Y, X equal to Z, this will then prove that Y is equal to Z because you can just do a simple substitution. That's one way to go about it, and to do this you'd have to show that X is a subset of Y and Y is a subset of X, in addition to X is a subset of Z and Z is a subset of X. That's how you'd get the equalities here, that X is equal to Y and X is equal to Z. So, going on, if we want to get a visualization of how this problem works, let's just do a quick Venn diagram then. If we have, say, A and B, we know that each one of these is going to be A minus B, B minus A intersection B, where each of these is only referring to their domain, of course. And this whole thing is going to be A union B, right? By definition, the symmetric difference is, so if we do A symmetric difference B, this is exactly equal to A minus B unioned with B minus A. So if we want to visualize at least the first two here, X and Y, we can show that if A intersection B is only concerned with the middle part, we'll just fill that in here real quick. And that's all that there is to A intersection B. But if we want to show A symmetric B, or symmetric difference B real quick, we can just highlight these, in which they will not touch the area of A intersection B, and we can see visually that at least X is equivalent to Y. This, however, is not a proof. We have to take the long route for that. But just to visually see how that works, there you go. So I'm rather going to do what I just described there, but there's an alternative way to prove this theory, is that if you do a cycle proof, to where if you prove that X implies Y, in which then Y implies Z, and then if you can finalize that Z implies X, you have a cycle. You can just cycle through the entire thing to get to where you want. To help visualize that real quick, I'm just going to draw this out. That this is definitely an option. If you start at X, you can end at Z, and if you start at Y, well, you can make a full round circle to come back to Y if you really want to. Either way, however you'd like to do it, it is up to you. So, going on to prove X is a subset of Y real quick. Let's assume that X is an element of A union B, which implies that X is an element of A, or X is an element of B. So there are three options that can happen with this assumption. One, X is an element of A, and X is not an element of B. This is perfectly fine. Two, X is not an element of A, and X is an element of B. And then finally we have, of course, just both of them. We have X is an element of A, and X is an element of B. If you wanted to write these out individually, you could, but I'll just doing exactly as it's shown, if we go back to the definition of the symmetric difference, we can find that A minus B unioned with B minus A, right? And then, of course, A intersection B is just going to be it's both. So going on to what each one of these implies, we can find that if X is an element of A and X is not an element of B, we can show that it satisfies part A of our symmetric difference problem. So it means this will imply that X is an element of a symmetric difference of B, right? And that's actually the same thing for the bottom one here. We have our A there, our B, X is an element of A symmetric difference of B. And then finally we have X an element of A and X an element of B. This does not hold for the first portion, however it is satisfied by the second portion of Y, where it's A intersection B. And this is only true for when it's both of them simultaneously. So we have X as an element of A intersection B. And by proving that, by proving these three, we can show that X is an element of A symmetric difference of B unioned with A intersection B. So here we have our first scenario completely done, but there's a little bit more work we can show to go a little bit further. So we've finished off our first portion that X is a subset of Y, but let's just show a little bit more work. If we know that each one of these, our three cases here, only satisfies one of these three, A, B, or C, then we can additionally show that this is also satisfied. So we can do a little bit extra here and show that X is also a subset of Z. We can't show Y is a subset yet, but we can get there. So if we know it can only satisfy one of these three, then, let me just look at my notes real quick. Sorry about that, I just got a little lost, but to continue on where we were, I'll explain this a little bit more. The reason why this worked here was because we were able to show that X is an element of A minus B, which is the first half of the symmetric difference portion. All right. But to show a little bit further, we can prove that X will only satisfy one of these three. That, I'll actually just write this out a little bit. X is an element of A minus B. X is an element of B minus A. That's what's happening here. So if we can prove one additional thing, that X is an element of A minus B, symmetric difference of B minus A, or I guess union, my bad. Additionally, with A intersection B, that if it can only satisfy one of these at a time, then we've also proven that X is an element of A symmetric difference B, symmetric difference of A intersection B, right? And that's kind of what's happening here. Only one A, B, or C can be satisfied at a time in this situation. So in this case, we have proven for that problem. On to the next one. All right, where we finished off on the first part of number one, we finally proved that X is a subset of Y and X is a subset of Z. We first proved that X was a subset of Y, and we found just a little bit more work would help to prove X is a subset of Z, so we just did it like that. So to go on, we're going to we have a little bit of two choices here. We can prove that Y is a subset of X, or we can prove that Z is a subset of X, because now we just have two. This is what we have done. So I think we're going to start with Y is a subset of X here. just to get us an equality at least. So if y is a subset of x, then we have x is an element of A symmetric difference B union A intersection B, right? Which then shows that x is an element of A minus B union B minus A, just the definition of the symmetric difference function, or x is an element of A and x is an element of B. Oop. So I broke down each one by one layer. So if we go down one more layer again, we'll find that x is an element of, I guess I should write that inside there, but x is an element of A, and x is not an element of B, or x is an element, not an element of A, and x is an element of B, or x is an element of A, and x is an element of B. So at this point in time, it's kind of a little bit trivial on how you would go about doing that, but one thing that we can notice is, like I showed in the first portion of number 1, we kind of have these same portions here that we talked about. We have the 3 possibilities for a union B problem. We have x is an element of A and x is not an element of B, x is not an element of A and x is an element of B, or we have both, right? Those are our 3 different possibilities, that x is in one or it's in both, right? So in this case scenario, it's kind of a little trivial on how many steps you would show. To me, as long as you show that you have these 3 options available and it's one, this, or that, because if we just get rid of these bars here, because we only have or statements, then we'd have x an element of A and x is not, oops, daisy, x is not an element of B, or x is not an element of A and x is an element of B, or x is an element of A and x is an element of B. Right? We have each case statement A, B, and C readily available for us. To me, this is enough proof to show, but I would ask a TA about this video or something like that if this would be sufficient enough, but I think this is. So I'm going to say now that this is sufficient enough that to prove that y is a subset of x. There we go. Alright, where we just left off was that we had finally proven y is a subset of x. And since we have both x is a subset of y and y is a subset of x, we have finally proven that x is equal to y. And in addition to that, we've also proven that y is a subset of z. How? It's because now we have an equality here. We can replace our x in this portion with a y. So let's finally prove our final portion, which is, and we can actually do it either way. We can either show that z is a subset of y, or z is a subset of x. Whichever way you take it, but I'm going to go a route I think would be simple. I'm going to prove that z is a subset of x. So if we have x is an element of, ooh, this is a lot. So with this, we can put parentheses around anything we'd want to make it simpler for us. So what I'm going to do is I'm just going to put parentheses right there. It's still the same problem here, but I just made parentheses to make it a little bit easier for me. So we have x is an element of A minus B union B minus A. Well, actually, let's break this down a little bit. Since we have a symmetric difference right there, we'll break it down a little bit slower then. We'll have A symmetric difference B minus A intersection B unioned with A intersection B minus A symmetric difference B. Right? So, and the one thing to visually notice about this, again, is that we're basically at what we had for Y, but just worded a little differently. If we look at this in a Venn diagram sorts, A and B, again, we have symmetric difference in the both individualized parts, and then we have the intersection in the middle. These do not share any elements, so just thinking ahead a little bit, we can know that these minus signs are, excuse me, not going to have any effect, right? They share no elements by default. They just don't. So let's expand a little bit more since we have to use set theory for our proof here. Let's do the left side first. So we're going to focus on number 1 here. Let's focus on number 1. So for number 1, we have x is an element of a minus b unioned with b minus a, and x is not an element of a, and x is not an element of b. Right? That's just what the intersection here means, and that's just what the symmetric difference here means. And looking at this, if we go down one more level, x an element of a, and x is not an element of b, or x is not an element of a, and x is an element of b. And x is not an element of a, and x is not an element of b. We can prove just by this point, since we don't have an and statement on this side for both of them not being a or b, we can then just think to ourselves and understand logically that there is nothing over here that would matter over here. So if you want to personally think about it, this side never happens on that side. So we can just completely get rid of this right half, and we're left with x an element of a, and x is not an element of b, or x is not an element of a, and x is, ooh, did I write this one wrong? I did, oh, my bad. Sorry about that. We've just completely gotten rid of this because there are no shared elements. There is no portion of this that relies on both x being not in A and not in B. X is either in A or it's in B. It's not both. And I honestly think, I don't even know if I should put an and statement there. I think it might just be a minus, but I digress. Going forth, this one just simplifies immediately down to a symmetric difference of B, right? Because the or statement here generally just means a union. We have both the first statements of that and that, so I think we kind of broke it down just to show what it was, but one is just equivalent to a symmetric difference of B. So let's go on to 2, and I think you guys can see where this is going, but just to show a little bit further of what's happening here. For number 2, we have x is an element of a intersection b minus a symmetric difference b, all that jazz. Again, if you can visualize that these do not share any elements, you'll be in the clear. But yeah, we have x is an element of a, and x is an element of b, and oh god, x is an element of a, and x is not an element of b, or x is not an element of a, and x is an element of b. So by distributing this minus sign through, you can kind of imagine just flipping it. So if we wanted to just flip it, we would just do that and that, get rid of that there, get rid of that there, and put the element signs in there, but we'll end up with the exact same problem as before, just switched around. And like discussed up above, this one requires both x to be an A and B, where this one, however, is kind of a dual case scenario where it's in one and not the other. So these do not share any commonalities at all. So we're left with just x an element of A and x an element of B, which is easily just A intersection B. That is left for that. So by finalizing what 1 and 2 are, we can rewrite it. So if we just rewrite it really quickly, which is equivalent to x is an element of A symmetric difference B unioned with A intersection B. And this is exactly why. So I guess I was a little bit wrong in saying I'd be saying Z is a subset of X. I led in the direction very wrongly. Z is a subset of Y. That's where we ended up at. Since we started in Z with our definition, by just breaking them up into two separate ones and bringing them back together as something that is exactly Y, we know we're done with the problem, and we've finally proven Z is a subset of Y. With that, we have a definition for us to use. We have both Y is a subset of Z, and Z is a subset of Y. Knowing the definitions for subsets, we can therefore finally say that Y is equal to Z, and if X is equal to Y, we can substitute that in, and we can say that X is equal to Z. Therefore, X is equal to Y is equal to Z, and we're done. Alright, going on to number 2, we have to prove or disprove the power set of A union the power set of B is equivalent to the power set of A union B. To go quickly over what the power set is, the power set of a function, or not a function, but a set, is equal to the set of all of the sets, so I probably shouldn't use A here. So we have set X such that X is a subset of A. It is the set of all subsets of a set. So just if A is equal to, say, 2, 4, 6, oops a daisy. Therefore, we have that the power set of A is going to have and the empty set, which is always in a power set. No matter what you take the power set of, the empty set's always in there. We also have 2, 4. It's basically all the possible permutations of it. And the last one, of course, would be 2, 4, and 6. That A is always a subset of the power set of A. A is always in itself, basically. But yeah. Going on to what the problem is asking. It's kind of similar to what number 1 asked us. So in order to prove this, we have to show that it is a subset in both the directions. So power set of A union the power set of B has to be a subset of the power set of A union B, and vice versa, if you want to prove it. So let's go along the path of proving and see if we come across anything. So if we have, we'll go first the left to right here. We'll get X is an element of the power set of A union the power set of B. Therefore implies that X is an element of the power set of A, or X is an element of the power set of B. Now, one quick note you should have here is that this is wrong. You cannot say X is an element of A or X is an element of B, because you're getting all permutations possible. So you could easily have the empty set. You could have other elements that, so as we go back to our problem earlier, A is equal to the set of 2, 4, 6. The power set of A has the set of 2, 4, which is not an element of A. You cannot switch it around when X is meant to be a set. So let's continue. From here, if we're able to say that X is an element of power set of A or X is an element of power set of B, this right here is the definition for a union. But I guess that's what that's doing up there. But we can find out that all possible outputs of power set of A and the power set of B can be shown that X is an element of the power set of A unionized with any other set. Any set, you will always have X as an element, or X is an element of the power set of B unioned with any other set, right? So this therefore implies that X is an element of the power set of A unionized with B, because any set you put in here, doesn't matter, it's the universal set, the empty set, or any set in that matter, it will always hold true because we have the power set of A in there. So we've gotten down to the first half of our problem here, no problems whatsoever. All right, so let's try doing the other way around then. So we have X as an element of the power set of A unionized with B. So your first thought might be to actually break this down and say that X is the power set of A, or X is the power set, or X is in the power set of B. And you say, hey, we're done. We got nothing else to do. This is wrong. You cannot break it up. You cannot take them out of the parentheses of the power set because, say if we have A is equal to, again, 2, 4, and 6, kind of showing a proof by, not contradiction, but proof by counterexample here. And B is equal to 1, 3, and 5. The power set of A union B is going to have the element, dot, 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 comma, is going to have the set 1, 4, 5. Dot, 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 because it'll have more. Neither A or B has this set in it, in its power set, because A doesn't have the element of 1, and B doesn't have the elements 4 or 5. So by default, this one, which is in the power set of both of these, or is in the power set of this, is not in the power set of these. So unfortunately, this is wrong. And we're actually disproving this. This cannot happen, this cannot exist, because, mainly because this statement here, and where we break up the power set, cannot happen in any shape or form. So in the end, we only got 1/2 the answer, but we were able to disprove it. And with that, we'll go on to the next one. All right, number 3 is asking us a very simple question. Let f be a function from all reals to all reals cross all reals to all reals, be defined by f of x comma y equals the square root of x squared plus y squared. Simple enough. And that A is a set such that an element x comma y is satisfying that 2 is less than or equal to x is less than or equal to 4, and -1 is less than or equal to y, less than or equal to 3. All right, simple enough. I just kind of rewrote what was being said here, and because if we had A is equal to 2 comma 4 in this case, then it wouldn't have an equals here, it would just have x is between 2 and 4. So and it's asking us to compute the image of the function of a. So what's asking for us to do is, in an image, we have to kind of give the bounds of what the range is going to have. So what all values are able to be had, kind of like what's happening with a here. It's giving all of the values possible for x and all of the values possible for y. So in this case, we'll have f of x comma y is going to be equal to z, which is equal to the square root of x squared plus y squared. So in order to give the image, let's first find the minimal value that we can get out of this function. So let's just plug in the two smallest values possible, so 2 and -1. We'll get f of 2 comma -1. We'll get 4 plus 1, so we'll have the square root of 5, which is about, well, it's greater than 2 at least. It's greater than 2. I don't know exactly what that is, but it is that. And you might think, okay, we got the minimal value, but this is where we'd be wrong, because y is squared, -1 is not the minimal value, because we'll still get a 1 out of it, no matter if we plug in -1 or 1. So in order to find the minimal value, we have to actually plug in 2 comma 0, which in this case will be square root of 4, which is exactly 2. This is our minimal value. So let's try to find our maximum value then. So we plug in just the maximal values. So there's no need for a trick like plug in 0 instead. It's just a straightforward one. You have f of 4 comma 3, which is going to be equal to 16 plus 9, which is equal to square root of 25, which is equal to 5. All right. So in this case, we've finally gotten our minimal and our maximum value. So we'll have the image of f of a is equal to 2 comma 5. And again, we're doing the square brackets here because it is exactly equivalent to these. If we had curled brackets, just parentheses here, we'd have an incorrect answer because 5 and 2 are both possible values we can get out of it. And with that, I believe that's all we need to do for the image of f of a, and we're done. We'll go on to the next one. All right, we're going on to number 4 now, which number 4 is saying, let f be a function from a to b and g be a function from b to c. A, prove g composed of f is a bijection, which implies that f is 1-to-1 and g is onto. All right, and then for b, is the opposite implication true? Is f is 1-to-1 and g is onto imply that g composed of f is a bijection? I will be going over A in this video, but I will have B as a take-home problem for you guys to do at home and see if you can work your head around it, because I think functions are probably one of the hardest parts of this class, especially wrapping your head around composition of functions. So I want you guys to try to work around that. So g composed of f is a bijection, so we're supposing that. Suppose g composed of f is a bijection, right? All right. We need to therefore imply that f is 1-to-1 and g is onto. So assuming that g composed of f is a bijection can be a little tricky on the mind. So instead what we're going to do is break it up into two parts. We're going to say that g composed of f is injective, or 1-to-1 in this case. All right. And so we're going to assume that f is not injective here. All right. So we're going to do kind of a proof by contradiction here. And so we're going to have two elements in the image of f. So we're going to have a comma b in f of was it a? Yes, in f of a. Or I guess just in a, my bad. and we'll say that f of A is equal to f of B. This is fine for us to do because we're assuming it's not one-to-one, all right? So if we plug it into G composed of f of A, or f, yeah, and this is going to be equal to G of f of A, which we're able to swap it out for G of f of B, which if you want to write it out even a bit more, it's G composed of f of B. All right. This is a problem because this is assuming that going against what we assumed. So we have G of f is injective and that f is not injective, right? We're getting a contradiction here now because these two are assuming that A is equivalent to B in this scenario. And we can't have that. So therefore, from our assumption, we get the opposite, that f is injective. All right, so this one is a little hard to wrap your head around, but just know we're able to say that A and B are separate elements in A, and we have that the function of A is equivalent to the function of B, as in they are not injective. It's not one-to-one. They don't have individual outputs. So by plugging in the G composed of f of A, we get everything else, including B, right? Which is kind of implying that A is equal to B if G composed of F is injective. All right. Going on to the second portion, we're going to assume that G composed of F is surjective, meaning it's onto. All right. We're going to let Z be an element in our final output, which is going to be some element in the set C, right? Because we have A is going to B, and then B is going to C. So C is our output of the entire function here. Then if G of F is surjective, then there exists a X in A, so all the way back to the beginning function, such that G composed of F of X is equal to G of F of X, I'm just writing this out, which is going to be equal to Z. That's what our existence here is kind of saying. Let Y equal F of X in B. So this is like the output of our function of X. Then G of Y is equal to Z. So therefore there's kind of just there's always something in our function of G or in the set of B that will satisfy our onto situation here. Therefore this will imply that G is surjective as well. All right, let's go on to the last one. All right, going on to number 5, our last problem here. We have, I'm going to do A. I'll let you guys do B and C at home because I don't think they're very difficult in finding a contradiction or even being able to prove it. But for A, we have A union B is a subset of A intersection B, which will imply both ways that A is equal to B. So to visually look at number A, let's just draw our Venn diagram here real quick. A and B. And looking at the left side here, if our intersection here in the middle is going to be the parent of a subset to A union B, which A union B is generally all of this, right, it's everything possible in A and B, then we know that there's something going on here, because generally A union B is generally, if you want to think about it, greater than or equal to A intersection B in size, and that'll be called cardinality when you guys get to it. But cardinality of A union B is usually greater than or equal to the cardinality of A intersection B. The reason why the equal to is there is because of this specific reason, but because for the problem A here, now going off course, we have to prove both ways, because it's both implying to the left and implying to the right. So I'm going to do right to left first. So we have suppose A is equal to B, or in set terms that A is a subset of B, and B is a subset of A. All right. So now we have to show that it implies that A union B is a subset of A intersection B, given this. So if A is equal to B, A union B is equal to A, and A union B is equal to B, right? Nothing wrong with that. And then additionally, A intersection B is equal to B intersection of A is equal to A, which is also equal to B, right? In this case, assuming that A is equal to B. So, and in this case, this is the only time where we can say this, that B intersection A is a subset of A union B, and A union B is a subset of B intersection A. The reason we're able to get down to this is purely because we have all of these equalities that we can swap things out. So A is a subset of B and B is a subset of A. We can swap out either A or B for what we need. So if A union B is equal to A, well, if A is the subset of B, then all of a sudden we have A union B, subset of B, swap out B for what we need, and we're all done for at least right to left. So let's go on and do left to right. We have A union B is a supposing A union B is a subset of A intersection B. A union B is a subset of A intersection B. And remember, visually speaking, this is what it looks like, that it's only happening in here. Our equality, or our subset, is only happening in here. Because generally what's happening is that A intersection B is a subset of A union B. That's why this is so weird. But to continue on, if we have supposing this, then we have X is an element of A union B, which implies that X is an element, not that sign. X is an element of A intersection B, okay. And so if X is an element of both of these, this therefore implies that X is an element of A. So it means going along with what's just right there, because we had to start here to go to here for that subset to get that extra information here. We'll go on another tangent and just say X is an element of A. This will imply that X is an element of A union B. Follow along from the one that we just made. X is therefore an element of A intersection B. It's going to imply that X is an element of B. And so You can do this for every element that's in A, and you can do this for every element that's in B. Whatever's in A is in B, and vice versa. So if we do that real quick, X is an element of B. This implies that X is an element of A union B, which implies that X is an element of A intersection B. And we're getting this because of this part up here again, which is going to imply that X is therefore an element of A. So all elements in A are in B. And all elements of X in B are in all elements, or are in A. And by proving that for all elements of X in A are in B, and vice versa, we can then say that A is equal to B. You don't necessarily have to have for all X, but just having some kind of X is in A, you have a bunch of steps, and then you get X is therefore in B for all, and you can do it vice versa. Then you can confirm that this statement is true. I'll leave B and C for you guys to attempt, and I hope you guys have a great rest of your day. See ya.